everyone. How's everyone doing? Alright. Welcome to another EE360 video. And today we'll be going over, computer assignment 5. And actually, before we even go through that one, we're going to go over the Laplace transform. And let's do this. So I will try my best to show you practically how to use the Laplace transform and what it means and why we have to learn it. So the Laplace transform, if we pull out this pen, is basically suppose you had some type of system. Let's see, like, some signal x of t, like, some variable signal, and maybe it has, some e to the yeah, let's call it alpha t. It's some signal. It's probably gonna look like this, or let's just make it some type of signal. It's gonna look like this as a function of time. Well, we can actually see if we can represent this as some type of signal in the Laplace domain, which I will try to draw like this. It's gonna have some real component. It's gonna have some imaginary component, and the parameter that we're actually sweeping is s. And this function right here, assuming that a is probably positive, it's going to be, and since it's real, maybe it's going to be here. And you're probably going like, whoa, David, how'd you know what this signal is going to look like or what's it going to do? So I will try to teach you the practical way of really what does the Laplace transform really mean, and also try to show you what it means in your systems. So this right here is probably something you will never see, or actually you have been shown once in the lectures, but this is the most practical way of interpreting these signals. It's harder to see it in the Laplace transform, but in the Fourier transform, yeah, I'll show you a lot of cool tricks right there. But I tried studying control theory for this, but this is the best I can show you. But we will try something simple. So from what I recall, I think if we had our signal x, then the Laplace transform of signal x, the Laplace transform, we're going to take it, we're going to completely destroy time. Time is gone, so we have some time thing, amplitude x of t. We're going to completely get rid of time. So that means we will have to, we're going to look at the entire signal, analyze the signal. Our signal is going to be like, oh, it's, some signal, assuming it's finite, which is another word. We're going to have to analyze the entire signal from whenever it began to whenever it ends, the time. So this is where the interval comes from. We're going to take our signal, the signal that we have, we're analyzing from the beginning of time to the end of time, the entire signal, trying to show you how to do this, where it comes from. And then we're going to multiply it by some parameter, e to the st minus st dt, which is we're adding each and every individual point, every point in time, adding them all up and then changing it into the s domain. So this right here would be your general Laplace transform, and how to turn it into something, something familiar. So Dr. Stevie will probably be teaching you the bare bones, like, the theory behind this, but I'm just going to go through how to practically use this and how to apply this to your assignments. So let's see if I can grab another piece of paper and show you what to do. You'll learn this eventually. There we go. You can see the bottom. I'm going to mark this as 2. So let me see if I can play with the following signal that I have generated here. Let's see. Let's look at your assignment first. Exit here. Where's the assignment? There we go. So the one thing I'm going to try and do is, oh, here goes my microphone. There we go. Stay. Let's do the following. Let's see if you guys can follow this. Let's see. dy of t with respect to time squared minus 7 dy of t with respect to time minus 12 y of t. So we're looking at analog signals. So all this is going to be a discussion on analog representation. So that's why we have the Laplace domain. There we go. My microphone would stay down. So equals, and you can probably see what's going on based on looking at the screen. Dx squared, or second derivative of x with respect to time squared, plus 7, no wait, no, 3. Yeah, I was looking at it wrong. Yeah, you can probably see what I'm doing. Plus 2x of t. So this right here is our system that we have. And there's one thing I want to show you, that it's a property. We're literally going to go through this assignment, and you're probably going to be like, well, what's going on? There's a couple assumptions before we apply or approach this kind of problem. This is a linear time invariant analog system. So it's all going to be pure analog, and you can build differentiators, integrators, and all those nice little things, adders too if you wanted to. Yeah, op amps. But we're going to assume our signal. So let's bring back the old box, you know, good old box. X of t, h of t, y of t. We're going to have our system, you know, and we're going to kick this box. We're going to kick this box so that everything that happens to the box, that kick that we establish, is going to be t is equal to, you know, 0 minus, or just 0. Let's just think about it. So we're going to kick this box, you know, at t is equal to 0. I could say minus, but that's going to get confusing, but we'll talk about it soon. And right, what we're trying to do is we're going to try to do the unilateral Laplace transform of this function that we have right here, this linear time invariant system. So one of the properties to go from the time domain to the Laplace domain is that, well, let me see if I can remember it. But now I'll just go through the actual practical. Oh, you guys can't see my screen. There we go. You guys are probably saying, David, we can't see your screen. There we go. Perfect. Nothing has changed much other than, well, I have this system right here, x of t, y of t. We kicked it at t equals 0. We're about to analyze it, but the one term I'm about to analyze right now is this term right here. So the rule that I remember from, well, that you will all memorize, hint, hint, is that we have this d y of t dt squared is going to basically equal to a transform. So y of s, and it's going to have a parameter s squared minus s y dy, I think it's y prime of 0, and then minus, I think this should be a regular. I think I remember. I should remember this. Oof, I can't remember this one. Point is, the reason why I bring this one up, you'll probably point out my mistake right here, but point is, we're going to have these little two conditions right here. They're at y of this. So actually, this is dy of t. We take a derivative. No, this should be that. This should be there. There we go. We're looking at when time is equal to 0, or this right here is an initial condition. This right here is going to be at dy of t is equal to 0 dt. And then this right here is actually, that's not even, y of t. And then this right here is dy of t at equals 0. But the point is, what I'm trying to get to you is, with the unilateral Laplace transform, nothing has happened before the kick. We're assuming the system is clean. There's no memory. So the whole point of this discussion is that all this is 0. All this is, it's gone. This is our initial conditions, and it's all equal to 0 for unilateral Laplace transform. So yeah, that was a long definition I had to establish there, because this is the practical way of solving these problems. So the point is we're going to have this little rule. You'll look at this rule later on in the class. It's probably going to be confusing for you right now, but right now we are trying to do these systems. So finishing this thing. But point is, this is the easiest thing you should memorize. This is all you got to memorize. When you see squared, you got to place a s squared right there. So what we're going to do is we're going to do an s squared of y of s. So this second derivative turns into an s squared, y of s. Then we have this minus 7. That's a funny 7. There we go. This one has a derivative. We replace it with an s. There we go. Then y of s. Or I'm thinking ahead of myself. Then minus 12. Well, that's just a regular time thing. And you'll realize later, well, the Laplace transform of y to t, y of t is going to be y of s. So that's really easy to establish right there. So that right there is our first term. Boom, you're done. Hooray. Just kidding. You still have one more thing to establish, which is these inputs right here. So the same thing applies with the outputs and the inputs. It's the Laplace transform of your input, the Laplace transform of your signal. So think of it like that. So this is how you approach it from this angle. So now we're going to do the equal sign. That's a nice color. Yeah, you can see it. We have this term right here. Watch, this is how you're going to do it on the exam, how you're going to do it on my assignment. Well, Dr. Stever's assignment, but I edited it to make sure that you know what's going on. This is what you're going to do. And you see this? Second derivative, you're going to do an s squared x of s plus 3 of s x of s, and then plus 2 x of s. And boom, now you have the Laplace transform of your differential equation, or your differential equations. So now the next thing we're going to do is, you see this, let's see if this is a nice color. It's an okay color. There we go. So we're going to substitute out this value. Ugh, I'm not going to use that color. It's a bad color. Y of s is y of s, this bracket, s squared minus 7s minus 12 is equal to x of s squared plus 3 of s plus 2. And now, from recalling this guy, what's the Laplace transform of h of t? H of s. That was supposed to be a trivial question if you didn't get that one. But now, one thing we're going to establish, or that I should have established. Let's bring out the other piece of paper. Is that, let me do this. We have some system y of t is going to equal x of t convolution of h of t. Into the Laplace domain, this is literally y of s, x of s, h of s. The convolution is multiplication in the Laplace domain, so that's a pretty nice tool, where h of s is equal to y of s, x of s. So this right here is what we're trying to establish. So going back to our nice little problem, you can see that h of s is equal to y of s, and actually let's just divide that right there. Okay. Yep. Yeah, let's do this. Y of s, x of s is equal to s squared plus 3 of s plus 2, s squared minus 7s. No. Oh, that's the reason why it should have been. Okay. Point is, what I was trying to do was establish these kinds of equations. That should have been plus from the beginning. I didn't even point that out. But what I'm trying to get to you is, if we had this kind of system, this linear time invariant system, analog system, that we can easily turn it into the Laplace domain by doing this little trick. And now we can start doing our Baire analysis. Right now we're about to do the Baire analysis on this. So whatever I said about these minus signs, yeah, don't worry, they're coefficients. So, but this is how you practically get to the Laplace domain. And now you're probably saying, well, now what do we do with it? So the next thing we're going to try and do is, well, let's get this out here. So we're going to try to establish the poles. H of s is going to equal s squared plus 3 of s plus 2, s squared plus 7s plus 12. And we're going to try and establish where the poles and the zeros are. So this is the next thing. So looking at this, 4 plus 3, s plus 4, s plus 3. And this right here is going to be s plus 2, s plus 1. And there we go. Now you're probably saying, okay, now what do we do with it? So next thing is, well, let's go into the Laplace domain and let's draw these out. So this right here is going to be the real part of s, the imaginary part of s. And I should have used a better color. Let's move that right here. So we have a pole right here. When does this go to infinity? And that goes into infinity when s is equal to -4. So that means -4 is going to be here. And then -3 right here. So we're going to have a pole right here. The real part when it's 4. And then the real part is going to be -3 right here. So I'll just do this right here, -3. So that's a pole on the real axis. Then we have a 0 right here and another 0 right here. But point is, this is probably what we're going to be seeing in the Laplace domain. And we're saying, okay, so now we know what our Laplace domain looks like here on a piece of paper. Now, what do we do? How do we verify these answers? So that's when we're going to start using MATLAB for our next thing. So before we go into MATLAB, I want to make sure everyone knows what's going on right here. This right here is right here is the minus side, the plus side, the positive real numbers, negative real numbers, positive imaginary numbers, positive negative imaginary numbers. But you see how they're all on this left side, left-hand side. And a rule that we have to establish is we're going to have to look at the region of convergence. We have to make sure that we converge at a really nice number. So the rule is we got to make sure we're looking on the right side of the rightmost pole, which is this guy right here. So this whole entire region is our region of convergence. Region of convergence. So that means everything we do here is going to be stable. Everything on the left side is going to be well, it's going to be a non-causal. This is the non-causal side. And here's another trick if you wanted to know. You see this, let me just circle that one right here. This right here is the entire imaginary axis when the real part is 0, but the entire imaginary axis. When the region of convergence has this axis, that means the system is stable. So that means this is stability, stable. And if we don't include it, that means our system is unstable. So make sure that your poles are on the left side of this nice little axis, and then your system should work, should be stable. So the next thing we're going to do is go into MATLAB. So look at the following screen, and let's pull out MATLAB. So making sure we get your money's worth. And the one thing we're going to do, and this is how you would approach this assignment. So we're going to try and look at a nice little transfer function, and let me get that right here. There we go. So the one thing we need to do is, well, actually, let's go back to our recording, or not recording, this video. You're probably saying, okay, David, what's this? What is this? What is S? I don't know what S is. And that's a great question. I would ask, like, how would you change S? So S is basically, well, you know, some real part plus some imaginary component. And this can be any value. This could be any number. And the one thing that okay, let's just get to the whole point of this thing is if we had some output, the theory is if we find the Laplace transform at S is equal to S naught, so any value that you want. So if you punch in a random, like, okay, s is equal to 1, Lamau, or whatever you want. So we're looking at s is equal to 1. So that's in the region of convergence. We're looking at what the system does. So if we plugged in a number into here, punched it into here, e to the minus st, and this right here is the parameter that we put in there, and that's basically what we can do. So if s is equal to 1, we punch in a 1 here, then like, oh, we get that one, and then we put in a 1 right here, and you can see that that's stable right there. So the whole point of this assignment is to make sure that we know what this is going to happen. So this s parameter is something you can just plug and chug in there. This will be weighted by whatever this is going to look like. So what we're going to do is we want to analyze every point of s. So we're going to look at, let's look at all the real values of s. So when the real values of s is from minus 10 to 10. So we're going to look at s is equal to minus 10, minus 9, 10, if you get that pattern. So we're going to look at this. However, s has also got an imaginary part. So the imaginary part of s, we're going to look at when we're looking at j of 10 all the way to j of positive j of 10. So that means we're going to look at s is equal to minus j10, minus j9, positive j10. And now you're probably saying, can't we just do this all at the same time? And yes, you can. So if you wanted to, you can do s is equal to minus 10 minus j of 10, plug this number into MATLAB, and then calculate this. And I think I'll show you that right now. So let's exit that right here. So let's do this. So what I like to do is, let's call it hn, and we can do, actually let's do this right here to follow what I have. S is going to equal minus 10 minus j, actually let me do this, real of s plus j dot times in s. So that's what I'm doing. You can do anything else, but this is what I'll be doing to show you. And let's say the real part of s, that we want, is going to be minus 10. The imaginary part of it is minus 10. And why didn't I put the j inside the imaginary number? For processing purposes, we leave j out of the imaginary number that I have circled right there, but you can, but it would cause a lot of problems. The format you should try to have is this, because this is easy to sweep up with a for loop. But I will show you a more technical skill, which is easy. So this right here is going to get stored. If you don't believe me, let's evaluate section. Boom. Now we have our s parameter. Hooray! We're going to sweep it. So what I'm going to do is hn is going to equal s dot time squared plus 3 dot times s plus 2, and hd is going to equal, because I'm lazy, oh yeah, there you go, whoo, that's going to be 7, and that's going to be 12. That's why we chose these numbers. Thank you, Dr. Stewart. And now we're going to do h is going to equal hn dot divide hd. There we go. And now we're going to evaluate that number. And what do we get? Boom! And we get a number. So that number that we just got, now we can use this number, multiply that by e to the minus st, and then boom, we get an output. So really not that bad. It's pretty cool. I'll show you another trick maybe in another video, but that's how you would do it. And you would do this for every point that you have. But the other thing that we have to establish is that we want to do power, and engineers like power. So if we want to get HP, if you wanted to call it, we're going to go to 20 dot times log of the absolute value of h. Or if you want, if you're scared about what's going on, you want to know exactly what's going on, you can do mag of h, or I don't know, hm, I guess, is abs of h. So you get the pure values, you get the pure numbers. So the output of this would be, let me get out of my mouse. The output of this will always be, well, real. Then let's get that right there, and we can replace this with h of m. And this right here, if you want to comment that to be power of h. There you go. And now let's look at that. And boom, now we have power. We have 3.8 decibels, which is a pretty good number. It's a pretty good gain factor. And now you got to plot every individual point that you have. But we want an easier way of doing that. So let's do the following. So remember how I showed you can do, oh, maybe we can do, let's do this. Vector -9 -8. And like, okay, if we do this, -10, -9, -8. Let me just show you the theory before we're, okay. So that means S is gonna, actually, let's just show you this. F9. Boom, now we have S is this, and oh, look, you see, pretty cool, right? And now we have those numbers, and then we can evaluate this again. And boom, now we have numbers, and you can see some pretty interesting numbers. So the other thing I have to do is, let's do clear all to make problems go away. So we're gonna do, so you see, like, okay, is there an easier way of doing that? Yes, there is. So if you want, let's do from 10 to 10, -10 to 10, in increments of 0.1 if you wanted. And then same thing with this guy right here. There you go. And now we have our two arrays. But now we have just, like, you know, a sweeping thing, and that means our S is not gonna look, it's not gonna look as cool as we want it to. Let me show you what S is gonna look like. S is, well, a vector. We wanted a square of this. So there's a trick that we can use, and that's mesh grid. So what I'm gonna do is, it's the real part of S, it's imaginary part of S. So what we're gonna do is we want to make sure we can map this. So let's do re and m and mesh grid. Re m. So what's happening here is we're looking at the x-axis. The x-axis, which we ideally wanted to go like this. We're gonna create a whole bunch of the same copy of this. So okay, let me just try to visually. Actually, I have a better idea. Let's grab the camera. So put a 2 there. No, this one right here is a 3. I'll show you with pens. There you go. So we're gonna have an X, and we're gonna have a Y. So these are two rows. And what we're gonna do, mesh grid basically says, okay, here's the x-axis, and we're gonna just tilt one like this. We're gonna create exact copies like this, and then the y-axis is gonna just create exact copies like that. So now you have a sweeping row of these things, and it just does that for you. So that's the best way I could have explained that. But in a nutshell, this right here will be a bunch of x values. This will be a y value. Just flips it, and then we'll have a square. And I'll show you that right now. Actually, let's do this. F9. Boom. Oh, that's because I called it. There you go. F9. Oh, no, not that. F9, there you go. And let me show you now. Re. There you go. And now you can see this right here. Well, oh, we can see, okay, this is our x-axis. Okay, like here's -10. And if we sweep right, and yeah, that makes sense. Like if we keep going here, we'll find the 0 point. There you go. So that right here is your x value is equal to 0. And then we want to look at the y's. And boom, that makes sense. So we can now map this in here. So if we look at this corner right here, this will be the parameter y is equal to, well, the imaginary is 10. That's, let me see if I can show you. So here it is, minus 10 in the x-axis, minus 10 in the y-axis. But now I'm like, okay, I want to look at something less real. So let's go this way to 51. So this is the x-axis is equal to minus 5. Let's look at 51. 51. And boom. So this right here just represents that thing that I just showed you is the x-axis when the real part is minus 5. The y part is equal to minus 10. So boom. There we go. So now we can do the same thing with our s. It does not exist. Just kidding. It's because we haven't established it yet. There we go. I'll erase that. Boom. And now let's create this. And there we go. As you can see, wow, we have numbers. Now the next thing we're going to do is, well, if we can do that with this, then we can do that with that. Now let's run that. Boom. We're done. So now that's the little first part of exercise 2. So that's how you do it. And I hope you guys know what's going on. You're like, oh, gee, David, that was... some people are going to give me for loops. Be careful with that. This right here is the easiest way I can show you. Hopefully that would make sense. So that's going to get started with the first 2 exercises. And now you're saying, well, David, what does it look like? Okay, I'll show you. And because I already have that established here, let's do that right here. Do the following. Figure 1. And mesh C, re, M, and HP. There you go. And then because I already have that here, boom. And because I like my function, where's my function? There we go. Pretty graph. Yep. And everyone likes a nice function thing. Maybe I'll show you a trick with this one. And boom. Oh yeah, what's that? What's that we have here? Look at that. And that right there is our Laplace Transform. Pretty nice. And you're probably saying, well, David, what's going on? And I'll show you what's going on. And let me bring out my piece of paper. And let me see if I can do the following. Okay, so, oh yeah, you're getting your education. So, look at this right here. You see this, see that we have 4, 3, wait, minus 4, minus 3, 2, and 1. And that was something we've looked at right here. This nice representation. Now, watch the following magic. Oh yeah, guess what's that? Look at that, minus 4. Here's the real axis, 0. Here's minus 4, minus 3, minus 2, minus 1. If you tilt it, you see? And then you're like, oh, David, now I know what's going on. If you know what's going on, if your picture looks like your hand calculation, that's why I tell everyone to please do your hand calculations. Make sure you know what's going on. And then, can you do it on a computer? And if you can do, you see, look how this computer did it nice. It analyzed every point. It's hard to analyze at a pole or a 0. Well, maybe a 0 because it's 0. But around the pole might be difficult. But using MATLAB, it's a powerful tool to be able to extract a lot of information. And if you wanted to tilt it like this, there we go. You can see we have a pole, we have a 0, and look right here. We have our 0 axis, the real axis. Everything before the real part is the real part's negative. Everything is on the left side of the imaginary axis, which means this system is stable. So that's how you do the first 2 examples. And Now you're probably saying, well, David, now how do I do the next example? So let me show you. Where's that assignment that I have? There we go. So now, the next thing I want to show you. And let's actually go back to, so we're going to look at this, and you're saying, what's this? So we're looking at omega. Think of it as like a coefficient. It's a coefficient, and you're looking at only the imaginary values of h of s. So when s is 0, so that's what I've noted right here. So we're looking at when s is 0, the real part is 0, and only the imaginary. So let me pull up handy dandy camera. So this point right here, this thing that I highlighted, that stable area, we're actually gonna take a slice. We're gonna cut right there, and we're gonna look at it like this, and we're gonna be like, ah. So before we actually do that, we're gonna predict what it looks like, and I want you to guys try this with me. So you can see right here, I have this little 0 axis. If we look right here, we can see that we have, like, you know, some little tunneling peak right there. Actually, it might be better if I looked at it like this. See how it looks like, you know, like this. It's kind of like down shaping. So that's what we're going to be expecting. How do we know? Okay, let's try it. There we go. So exercise 3. And we're going to look at what I like, the Fourier transform. And it's a beautiful transform. I really like it. It's probably one of the best transforms out there. Just kidding. There you go. And see if I can do that first half of the assignment right now. Get you guys going. It's a really fun assignment. It's probably one of the most powerful assignments I've seen. There we go. So let's look at a value omega. Minus 10, 0.1, 10. And you're probably saying, why did I choose 0.1? Well, because I want more points. More data, it's more fun. It's precise. It's pretty fun. Don't go too precise, because then your graphs start looking pretty heavy. You don't believe me? Let's try it. It's out of 0, 0, boom. Woo! Look at all that processing. It's a lot. Oh gosh. Looks like I crashed MATLAB, guys. So that's what you get for, well, that's what I get. Hopefully it doesn't crash. Okay, that's why everyone's got to do 0.1. Don't do what I just did. MATLAB, are you okay? Well, while that's calculating, so the whole point of this is to show you that. Oh, there he goes. It came back. MATLAB, are you okay? There we go. Woohoo! And look at that. Oh, it's so heavy I can't even carry it. Oh. Hopefully I didn't crash MATLAB. There you go. Oh, that's a heavy graph. This is what the Laplace transform will look like. And now you can see it's much more defined. Ooh, it's so heavy. I think MATLAB's crashing on me. There we go. All right. Let's do this. Let's go back to what we had. Boom. Easy to analyze, okay? Okay. There we go. Omega is equal to 10. Let's do this. So what we're going to use is the Frex equation. So Frex, or Frex, I call it that, is expecting some, you know, h num, h den, and some parameter. And this is going to give us h, that I will call hw, h omega. So what we're going to have to do is, well, it's expecting h num to be some vector, which is going to be 1, 3, 2. And this basically is the S representation of it. So if I were to look at the leftmost side, that's our S squared. This is our S1, S0. So that's how you do that. H den is going to equal to 1, 7, and 12. There we go. Don't forget to terminate your stuff. There we go. And let's terminate that. And what did I do here? Mag, mag HW abs of HW, and let's do HP power, H omega power is going to equal 20 dot times log of mag HW. There we go. And one thing you got to note about the H parameter, the Laplace transform, is that if we have an imaginary number, we're going to have some type of angle. This is going to have to create some type of angle. We have a, right here, we have a, if we do a imaginary square, we have some type of angles. We're going to have some type of change of angles. So that's what I'm going to try and show you right now. So if we want to get the angle, all you got to do is, well, angle of H omega is going to equal to angle of H omega. That's it. However, I like the good old degree system, so we're going to do dot times 180 degrees per radian, which is pi. So that's right. That's how you convert degrees. And now let's plot it. Figure 2. Hooray! Subplot. We're going to do 2 rows of 1 column in the first cell. Plot. And yes, you have to use plot. Don't use stem, because then your plots look weird. Plot. Omega. And then H omega P. And subplot. Second row. 2. Plot. Omega. And then angle H omega. There we go. And actually, let's call this title. Actually, I got it right here. Let's try to make sure this video is a little short. Go. Yeah, let's do this right here. And then angle of H, title, H of S, H of J, omega, actually okay, H, J, omega, go, interpreter, text. There we go. And then let's do this. Boom, boom, angle. There we go. Look at it right there. So that's how you do it. And you're probably saying, hey, why? Actually, let's pull out this guy right here. Yep, I'm doing your guys' assignment. How does this feel? Feels great, man. Keep going. Great. There we go. Now it looks more pretty. So as you can see, we have our power, and it looks like that little valley. And then look at our angle. Oh, and this is something you're going to have to eventually learn when you get to your upper division classes. And that is that this phase is actually not linear. It's actually pretty curvy, which means our system is distortion. We have distortion in our signal. So if we were to put in a square wave, it'd be kind of mixed. So that's how you do this if you know how to do this. But this is for this system. But I want to show you that we got this valley, and we have this right there. Does it look like it? Oh yeah, it kind of does. But if we were to just analyze this zero part, that's how we get it. So that's how you do example 3. So now example 4 is, let's actually look at it. And yeah, this is a really fun assignment. It's one of my favorite assignments. Back in the days when I took this class, this assignment, I was like, everyone was just copying. I didn't even understand what S was. I just didn't know. So, but I'm hopefully going to show you guys what's going on. It's asking for the roots, and it's saying it's determine the system's functions and poles. So that's easy. Let me show you that right here. And actually, I probably just might copy it right there. Boom. So the thing I'm trying to get to you, everyone, is yes, I'm doing your assignment. Well, I'm not doing the assignment. You can do a little change if you want to. Have some fun. But I want you to understand what practically is going on. Like the Laplace transform. Okay, I'm not a controls guy. But it's a really powerful tool. We can look at it and we can say, oh, this is what it does, this is what's going on. And we know what's gonna happen. So I want to make sure everyone knows what's going on. So here is the zeros of h and the poles of h. So all we're gonna do is we're gonna use roots h. Actually, do I want to do that? Nope. No. What I have is h of. Let's use this one. Yeah, h. So what roots is expecting? Roots is expecting a vector. No letters. So let me look at hnum, num, whatever you want to call it. 1, 3, 2, which is s squared plus 3s plus 2. And then same thing with them. And let's run that section. Now you see how it says zeros h, poles h. So if you wanted to, and if you wanted to make me happy, and happy me means happy grading for you. F print F the poles of the zeros of h. Can I do LaTeX? Oh, I don't think so. H of S. Yeah, I start loving it. LaTeX are located at D and wait, S is equal to, everyone's gonna have amazing assignments after this, S1 and S2, and then it's expecting the first parameter, which is zeros h1, zeros h2. And because I'm paranoid that it might not work. It works. Oh yeah. Oh, that's one thing we got to do. It's gonna look ugly. So what we're going to do is right here. See how we have this nice empty space? We're gonna do n, which is new line. I think that's what it does. Woohoo! And if you wanted to do this, woohoo! There you go. Now you have some really nice curves, and you see S1 and S2. Let's look at our graph. Here's our zeros, 1 and 2, minus 1 and 2, woohoo! Now, because we're lazy, and we're not lazy, we're just trying to get this assignment done. Poles, h of s, and you could do s of 1, but I easily can tell if anyone's just copy pasting just like me. S2, S4, I'll do that. Actually, okay, to make it more formal, SZ, where'd it go? Z, oh my god, Z, and then let's call this one P1, P2, because that's how we do it. And hopefully, I didn't make that one easy. Let's call it poles, 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 boom. Oh, there we go. Actually, because I don't want that, let's do this. There we go. You can do this and then this, and it make your assignments look clean. Run, 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 run. Zeros of h of s. There you go. Looks pretty clean, right? And does this verify our hand results, our hand calculator results? Look at that. -4, -3, -2, -2, and then minus 1. And there we go. Everything is working. We're understanding what's going on. Our MATLAB is being super helpful. This is the whole point of getting you guys, like, you know, prepared with the first 4 assignments, because the 5th assignment is where everything starts coming to play. So that right there is example 4. Now, the next thing it's asking for this assignment is, now that we found those zeros, pull this one right there. Now look at it. Does it match? And that's what I try to say. Using the TF2ZP function, now we need to generate the factored form of this system function. So it's basically, well, we want to see the actual poles and zeros. So our transfer function, so our s squared, s and whatever, turn this into polynomials. It's pretty cool, polynomials. So because gotta save on time and memory, make sure this video gets posted soon. Get that right there. Exercise 5. Let's call this one TF2ZP. Boom. Is that it? Oh wait. Oh wait, no, that's something completely different that I did on this side. Don't worry about that. Ignore that one. There you go. I'm so dumb. There you go. Boom. So now we're gonna look at the zeros of H, poles of H, and whatever K factor of H. And we're gonna erase this. That's from a previous assignment. And I kind of forgot what TF2ZP does. So help TF2ZP. And let's see what it does. K is just some gain factor. It's a gain factor. So if you were to multiply this into a gain, B0 is equal to this. It multiplies your gain, multiplies the whole thing. We're going to have some form of this. And now you know exactly what's going on. So let's test that out. Let's unsuppress that. Boom. We have a gain of 1, so that's practically gone. We have 2 zeros. Ooh, see? It works. So you can use this to analyze your system. So if you had some crazy concept, like maybe I'll just do it like this. You have S3, or actually if you had some system, let me just show you on a piece of paper. There we go. It's better to show you by example. That if we had some, you know, S3 plus S2 plus S1 plus, I don't know, 2S0, that if we use ZPK of, well, actually, divided by S4 plus S2 plus 3. If we did the zeros and poles of this of TF transfer function to ZP of, well, this is HN, HD, and HN, HD, where H of N is equal to, well, 1, 1, 1, 2, and then this guy right here is 1, 3, 2, 2, 1. If you did this, then you'll find everything, and it'll give you all the information that you need. This ZPK will be in terms of this function right here. So that's something really good to know. This is how you practically want to know what the Laplace transform is, how to get into this form. You're like, oh, once you have this form, you can build a z-plane domain. And that's the next thing we're going to do. Let's go into example 6, and that's what I have prepared for you right here. Actually, before we do that, there's one thing I forgot. So now it's going to ask, okay, now using the ZP2 transfer function, convert the factored form, so these poles and zeros, back into the actual transfer function. The, you know, S3 plus whatever you want it to be. So let's do that. And because I gotta cut on time, let's do this. Suppress. Actually, if you want to show me a really nice document, if you want to make it really nice on me, because it actually does, you can do fprintf. I will try to do this, but I won't complete it too much. Actually, yeah, we can actually do that. ZH. Oh yeah. Look at that. You see? That's what gets. What we get. Oh yeah. Boom. And then if you wanted the gain factor, you could have done that too. And let's just run this for now. F9. Boom. It's the same thing. Same values. You could show me the K value, but that one's 1. Unless you do the gain. The gain of H of S is K is equal to D KH, and let's run that. Oh, yep. Actually, let's get rid of that. This is going to be a great start into your assignment. Gain of H is 1. So that's how you do that one right there. And now we're going to take this and we're going to convert that back. So zeros and poles and Ks. And now we're going to return that back to boom. I could tell you guys to do something crazy. If anyone wants to do this, I won't recommend it. H of S. It's really dumb. Don't do this unless you really want to show me what you got. It's going to equal D S squared plus D, no, yeah, D S plus D. There you go. This is gonna be a lot. 0. Wait, no. Oh wait, yes. HB of 1, HB of 2. Yeah, don't do this unless you really want to. You really want like really nice MATLAB stuff. Let's run this one. F9. Boom. You saw what I did there. Actually, oh, that's because I didn't put the percent sign in the right side. There we go. Let's copy this. Go, run section. See that? Oh yeah. If I could write in LaTeX, boom. It looks like what we had from the beginning, which is, if I can pull out the good old piece of paper. What's it look like? Oh yeah, it looks like what we have here. So if you want to do that to make yourself happy, go ahead, be my guest, whatever. That's how you do the entirety of example 5. Now example 6. And we're about to hit the hour. Don't want to make everyone go crazy on this. And all we're going to do for example 6, z-plane, is, well, z-plane. There you go. Figure 3, z-plane. We're going to take, well, what's z-plane do? I don't know. Let's figure it out. Help z-plane. And what it does is, well, that's bad right here. I'll show you a better way of doing this. Z-plane MATLAB. And this is what you guys should be trying to do. Research. And oh, z-plane is expecting some B and some A. Let me see if I can zoom that in. Expecting B's and A's. Ah, as in our transfer function. Boom, and it creates us. You see the circle right there? It's a unit circle. Do you think we're going to see that? I don't know. Let's try it. Boom. Whoa. Look at that. And this is hard to tell, but that right there is a 4. All right, there is 3 minus 2. And does this look like what we have right here if we were to do boom? Look at that. You see? Try to make sure you guys get your money's worth. You know what's going on. This right here is the unit circle. So that's how you do it. Looks pretty cool, right? And you can get a lot from this. And you're like, oh, here's the real axis. And if we do this, oh, we can sweep air. If we look into the real domain, yep, nothing there. Oh, we got poles right here. Do you know what's going on? Oh, good. Just kidding. Yeah, you're getting ripped off. Now, the next thing we gotta do is, let me see. There you go. Exercise 6. Now we gotta use the residue function, and now we're about to do the final step of the Laplace transform, the whole point that we're doing this. And I want to show you guys some theory beforehand, before we actually get into this. It's a really important concept. And the whole point is, if I have some type of Laplace transform, like, you know, h of s, if I had some h of s, and I were to put, if I had some drawing, like you saw those drawings, like maybe it was looking like, oh, here's a pole, and here's a pole. That's a bad drawing. Let's do this. Whatever. 0, 0, pole, pole. If I were to calculate any value of s, like let's pick an s right here, and then if I were to do y of t is equal to h of, let's do s of 1 at e to the minus s of 1 t, then we get some function. However, if I looked right here at something that's the complex conjugate of 1, here's the imaginary axis and here's the minus imaginary axis, we know that if we add these two signals plus h of s of 1 complex conjugated e to the 1, there you go. If we add these together, these are going to cancel out. Their imaginary parts are going to cancel out. And then the real parts actually add up. However, because of this heavy scaling, this right here is dominating. It's a huge dominating force. This right here is going to completely destroy these points that I just plotted here. So if we add every individual point that we see, our scaling factor h of s, analyzed at every point and added it like so, right here, that all these things right here don't matter. It just completely goes away because they're like really small. However, these factors right here pop out. Actually, there should be a positive. I completely apologize to that. This should be positive because these values, this right here has a value. If we were to use the Cauchy theorem, which is basically the Cauchy theorem that I remembered, is if we were to do a Cauchy integral around this, that we have to get the residue. We get the residue of whatever's around this pole, and then the residue of this pole, and well, these are zeros. So the whole point is, what I'm trying to get to you is the Cauchy integral, which is basically if I were to take, you know, some integral of whatever this pole is, like, you know, h of s, we're going to get that value out. And from what I was saying about this, you're adding all these plots. I think the y of t is going to equal all the values of s from minus infinity to plus infinity. However, we got to analyze it at some value a. We're going to look at all these values. If we added everything up of h of s e to the st, there we go. That's where we get that number. Is that right? I think that's right. Yes, ds. However, we got to make sure we do 2 pi I, because if we do this, this type of number, we're going to actually get 2 pi I if we have a pole. We have a pole plus it has some residue. I think residue. So this is where this value comes from. This is from the Cauchy integral. So this value, this 2 pi I, comes because of this when we do complex integration, and plus some residues. So what we're going to try to do is we're going to try to find the residues of these values such that, let's do the following. Okay. Let's go here. So exercise 7, because we are running out of time. Get to here, copy, paste. Here we go. So we're looking at our numerators, we're looking at our denominators. We're going to look for the residues. And boom. What do we have here? And I'll try to write this down for you. And go, that was page 5 right there. To this. I want to make sure everyone knows what's going on. Okay, but let's pull this guy down. And let's do this, because I need to know what's going on. Actually, before we even do that, what does residue do? Help residue. Actually, it's better to show you here. Residue. Oh, look at that. It's already in my search results. This is what it's doing. We're going to have R of n plus some gain factor k. So that's the form that we have. So let's do the following. So the first value of h of s, the residue is we're going to have some minus 6, s, and then we have a pole at minus 4, so that means we got to do plus 4, and plus the next thing we got to do 2, and then s plus 3, and then plus 1. And that's it. That's basically it right there. Is that it? Yeah, I think that's it. But that one term kind of bothers me a bit. We're at 1:07. Because what I'm trying to get to you right now is, if we take the inverse Laplace transform of this, h of t is going to equal, well, the Laplace transform of that, so minus 6 e to the minus 4 t plus 2 e to the minus 2 t. And I'll have to figure out what that does. That's going to probably be some input. I'm probably forgetting something really. Actually, this can be ignored. We can ignore that for now. But let's do the following right here. There we go. I already have some. Actually, what I did right here was something you guys should do. Right there. Actually, yep. Run. Aha, there we go. And that looks like a pretty stable system to me. I think that's how it works. Huh. There you go. Apparently someone maybe multiplied this by s already. Yeah, that's because the one thing that I was thinking about was if we go back to what's that old note that I had? Boom. If we look at this function right here, if we multiply this by s, the final value theorem, this goes to 0, which makes sense. So that means, well, that's an impulse response. Actually, this system's stable. It's really stable. I think it doesn't actually do anything it has. Yeah, actually, that's it. That's it. So if you can do this, you'll be fine. However, your assignment, let me show you right here. And because I've seen this in the field a lot, your assignment is actually a resonator. This right here is the basics of a resonator. So you're actually going to have values that are bouncing up and down. So might vary differently, but do let me know what's going on. So that's how you do that. And where did I get this? Cough, cough came from, this piece of information right there. And that's actually something I want to see. Let's actually, I want to do this one. Let's do that one. HNum 1 to 2. No, wait. Yeah, let's see what it does. What did we do here? We're taking the first 2 points. Yeah, let's just brute force it. 1, 3. Check this. S and 3, yeah, that's it. Yeah, that's it. Well, never mind. That one's a bad system. There we go. But that's how you do exercise 7. And then exercise 8. What you're going to do is you're going to have to do some type of convolution. So that is the next thing I will show you. And hopefully it doesn't get too bad. Let me show you with that system that I had. And I'm assuming everyone knows what's going on. No, we don't. Oh, it's okay. So we're going to have some y. Oh, I can't even show you the camera there. There we go. Y of s is going to equal, well, what we're going to do is we're going to have some input, which I like to call input of x. It's going to be a unit step. We're going to have some unit step. Well, we already know that the Laplace transform of this is 1 to the s. So all we're going to do is h of s, x of s, is multiplication. So literally what we have, let's bring out the good old assignment. Okay, because we all like rewriting stuff. S squared plus 3s plus 2. And then square plus 7s plus 12. And 1 divided by s. So what the assignment means by convolution, it's not talking about it in the time domain. Convolution is basically multiplying of the polynomial. So if we were to look at, okay, if we were multiplying this by this, let's not even think about convolution. Let's think about what we're trying to do. So this answer is going to be s squared plus 3s plus 2, s3 plus 7s squared plus 12s plus s. So the convolution basically does this. If we do conv of h d and then 1 and 0, this 1 and 0 just basically represents this in a vector form. It's all, the output is literally going to be 3, 2, 1, 0. No, you know, 0. There we go. 3, 2, 1. 3, 2, 1. There we go. That's why it didn't make sense. Ah, sorry. 3, 2, 1. There we go. That's how it's going to output you this, which is basically, well, the convolution of this. You have 3 terms, 1 term, you convolve it, get you 4 terms right there. So let's do that right there. So now that we know what we're going to put into our nice little thing, let's do the following. Go. Oh, forgot to copy that. Here's example 8. Boom. So we're going to convolve the denominator. And is that what I called it? Yup, hden. And then the numerator of our output is, well, that's going to be it. There we go. Hnum from a previous assignment. And because we can't even see that. And because I have OCPD, numerator, denominator. And there you go. Ah, I see, making sense. And now we're going to do the exact same game that we've been doing it all this time. And that is doing the residue theorem. And there we go. The numerators, the denominators. We're looking at the residue. I don't know what it's going to do. Boom. Oh, look at that. Ky is gone. Nice. And now we have values for ry. So let me just do this because it's annoying me. Go. We have ry, p of y. This is the poles. This is the residues. So I'm going to write this on a piece of paper to make sure you know what's going on. There we go. 6. I want to make sure you guys are knowing what's going on. Okay. Go. Oh, you can't even see that bottom number. You'll actually. Whatever. It's okay. So y of t. So what I'm trying to get to you is we have this Laplace transform. If we add every point into y of t, we're going to have this nice function. Point is, these values here don't matter. They're all going to cancel out because the one thing that's really going to be the weighing factor is this pole, and we're going to have a 0 and a 0 somewhere going around there. These things will dominate so badly that everything here just goes to like nothing. It's not, we can neglect it. It's small. These poles are the huge dominating factors. So what I'm trying to get to you is the poles are the most powerful thing in the system. It's the thing that considers your thing stable. It's going to equal 1.5. Actually, y of s, 1.5 s. Then our pole is going to be at -4, so that means +4, plus minus 0.666 s plus 3, because the pole at -3 means that has to be s plus 3, then plus 0.166 because I want to at s. So there we go. Can you tell me, guys, how to go into the time transform, the time domain? It's really easy. 1.5. What's the inverse Laplace transform of this? E to the minus 4t plus minus 0.666 e to the minus 3t plus 0.166 e to the minus t. There we go. We're actually that can actually be debatable. Actually, no, I think it's just t. Can it be t? Oh, we'll figure that out. So the one thing I want to do to test that theory is the following. Go. Let's call this one y. And ry. Py. Why did I call it pk? Py. There we go. Let's see what that does. I forgot to actually plot it right here. Oh. Actually, I think I have it. And there we go. That right there is a step response. So if we put in a unit step, that's our value right there. So now, just to verify that this is actually the solution, and to verify what I did on my hand calculations right here, we're gonna actually do this. So let's do this right here. So I'm going to call a function y2. It's going to equal r of y, the first point, dot times exponent of py of 1 dot times t plus, because you guys can see a pattern, ry2, py2, and then let's do the same thing right there. ry3. Oh god, come on. 3. So that means if you guys can look at this, this should be a positive then, which I guess works. Let me just verify that. To 0. No, it's just the gain factor, because if the pole is 0, that means this right here is 0. So that means to verify this value, let's actually do it. Let me just do this. F9. And yeah, that's 1. That was their verified one. So yes, this right here is just the gain factor. So this is just 1. So now let's verify this one. You guys don't believe me? Y2. Actually, figure 6. Boom. Does that look the same? You guys don't believe me? Look at that. And that's why the residue theorem, the Cauchy theorem are the most powerful techniques. If you have these in your arsenal, in your little belt, you can do a lot of things with system processing. So, point is, yes, you can. If you were going to go back to our happy little thing, if we were to put this one, if you were to add every individual point, yes, you can do that, and then you can do the 1 over 2 pi I of c of h of s and e to the st. If you wanted to do this, you can, but that's a lot of pain, because with the residue theorem, the only thing that will pop up is these poles with their residues. The poles have a little stingent residue, so that's how you do the first half of these assignments. So with that, yeah, I think that's about it. I will show you the second half of the assignment. Actually, I think looking at a heads up at the second assignment, it is going into state spaces. Exercise 9, you're drawing a direct form 2 block. I want to see, well, you're going to draw your nodes, and there's 2 ways of drawing it. If you want a little hint, okay, I'll show you guys a hint on how to actually approach that one, and then you guys can start on it. David, I don't know how to do it. It's okay, don't worry, I'll get to you. There you go. So we had some system, I'm just gonna call it dy dt plus y, don't do this to me, microphone, dy dt plus y is equal to x dx dt. Does that look like your assignment? Yeah, it's close enough. Yeah, you guys can do this. Here we go. Plus x. That, if we do a double integral, let's actually take an integral of everything. If we were to integrate the whole thing, I'm going to leave that right there, is we get dy dt plus y of t plus y is equal to x plus x. If we do this another time, this is how I want you to show your work. Y of t plus integral of y plus double integral of y, well, you're doing double integral, is equal to the integral of x plus the integral of x, double integral of that. So that means we know how to build this. Integrals, integrator. This right here is easy to build. If you wanted to do this, y of t is equal to, well, integral of x plus x, and then minus y minus, you can easily build this one right here. So if I were to draw something right here, this x has to be integrated to give you, well, that integral of x. So that's basically the start of what you can do for the assignment. So I'll maybe go over this again, but that's how you get started on. And yeah, I think everything should be the same as the first couple assignments too. So I think you guys can get this done before this week. So make sure you guys do the assignment on time. And if there's anything I'm missing, I'll probably teach you guys more of the practical Laplace transform. But this is a really good assignment. Hopefully you guys understand it. We did an example, and hopefully everyone does the homework on their own. So with that, I think that's about it. Take care, everyone.